the timing track. So my name is Francisco Girela from the team at Safran, working on high accuracy timing and white rabbit solutions. So in this case, in collaboration with the team from OCP, Meta, Julian, and Armando from Meta, we have been exploring ways to minimize the impact of asymmetry in the link using a new configuration for SFP transceivers that use single wavelengths and single fibers. So before getting into the testing that we have done, a few words of introduction. So in timing, we typically use a lot of relative terms to describe how well we perform. So we are high accuracy, low noise, very stable, all relative terms. So with relative terms, what happens is that they evolve over time. And as we work in technology, we keep evolving. Nowadays, the situation has changed a little bit, as for the first time, we have a profile called high accuracy profile, so using a very relative term. And this profile is now part of the PTP, or the IEEE 1588 standard. This profile is intensively based on White Rabbit, and White Rabbit, when it started, its definition included goals in terms of performance. So when we are speaking about White Rabbit, it's sub-nanosecond accuracy on the time synchronization, below 50 picoseconds on the frequency distribution. So now that we have high accuracy in this standard based on White Rabbit, and we start seeing more and more applications actually aiming for sub-nanosecond accuracy. We had yesterday a talk in the quantum track on how they use White Rabbit to synchronize quantum networks. But we also see that in telecom and more in some data center scenarios. Even when the high accuracy profile doesn't define an accuracy level, the de facto meaning of high accuracy is more or less sub-nanosecond at the moment. So if you were happy with your high accuracy, hundreds of nanoseconds kind of solution, well, I'm sorry. So let's get into the problem that they initiated this kind of research. So we have network protocols that do the time synchronization. They are based on sending packets and time stamping when you transmit and when you receive them. And basically what you do is you measure the propagation delays, and you trust that the propagation delay will be the same, symmetric, in both directions. And thanks to that, you calculate the offset between the different nodes that you are trying to synchronize. White Rabbit is a high accuracy profile, but it's based on PTP. So the same that NTP or regular PTP implementations, it gets affected by this kind of asymmetry. In White Rabbit, a few things were incorporated to calibrate for that asymmetry and try to compensate for it. But still, it's an open issue, the same that with any other protocol. When we are trying to go high accuracy, there are different factors that we need to consider. So I have classified them in 3 different categories. The first one will be endogenous factors, which are related to the way you design your endpoint. Okay, so the White Rabbit devices that you have in each one of the ends of the synchronization link. So things as the precision and accuracy and granularity of the time stamping that you are doing of the packets that you are transmitting and receiving, that's important. That will be like the baseline of the accuracy that you can achieve. Some other things, like as we are transmitting these packets, we need to know the latency that we have between the time stamping unit that we use to make the time stamps of those and when you are actually distributing those packets, or on the opposite direction, the latency between the arrival of that packet to your unit and then the moment you time stamp. Okay? So that kind of information, it's important, and if it is a deterministic latency, you can compensate for it. And then there are other things like delays, calibrations. So you have a delay from the time stamping unit to the moment you send and receive the packets. You have a delay within the FPGA design. You have a delay on the pulse per second output that you are probably using for calibrating the unit. So a lot of components that you need to take care of. Then, second category, we have exogenous factors. So these are not related anymore to the White Rabbit devices endpoints or the timing nodes that you have. They are related to the technology that you use to transport the timing packets from point A to point B. Okay? So starting for the transfer technique that you are using. You have wire, wireless, optical, electrical. If you are in the optical field, which is the most typical one in data centers, you have single fiber, dual fiber, single mode, multi-mode, bidirectional, unidirectional, OTN, DWDM, dark fibers. You pick your poison, right? So apart from that, depending on the optical transfer technique that you are using, you will have different elements in the way actually creating that link. SFPs, optical fibers, dispersion compensation models, amplifiers, OTN system, DWDM, multiplexers. You have a full set of hardware that you will need to transport your packets or go through with your timing packets, and that will impact the accuracy. And lastly, we have the asymmetry itself. So the asymmetry can be caused by different things. One of the most simple ones to understand is that if I have two fibers, one for transmission, one for reception, they can have different lengths, different distances. That's an asymmetry. So that's, for example, one factor that will have an impact here. The same, that could be, for example, the accuracy that you calibrate, that you use to, or the technique that you use to calibrate the link, that will have a final impact as well on the performance. And then third factor, what I call common factors. These are things that apply both to the endpoints and the transport that you are doing, and that will affect the performance. So things like changes on temperature, humidity, airflow, vibration, or things related to the hardware, like aging of the oscillators, of the SFPs that you are using, they will have an impact. That impact, it's noticeable. This graph shows an excursion of around 25 degrees and how it impacts the propagation delay, in this case, the round-trip time of a timing synchronization, right? So we are lucky here, and we are more or less able to compensate that on the time synchronization, but still, it has an impact. And if you don't take that into account, this change on the propagation delay, which is in the hundreds of nanoseconds field, will have a direct impact on the time offset. Okay. So between all these factors that affect the accuracy, we decided to experiment in some of them. And we decided to do that testing this new single fiber, single wavelength SFP that basically transport over a single fiber using the same wavelength in both directions. What we expect with this is that we will be able to remove asymmetry because of the physical distances using two fibers, and we will be able to remove the asymmetry because of using different wavelengths that will have different propagation delays in both directions. And we think also that this can help us when we are doing, when we are experiencing these common factors, because the common factor will affect both the transmission and the reception as we are using the same optics. So we set up an experimental test for it, two White Rabbit devices connected by a 20-kilometer fiber spool. For us living in the US, that will be around 13 miles. So, and what we did is connecting the outputs of both White Rabbit devices to a time tagger, which is basically a way to measure the offset between the pulse per second signals, okay? And then we had a thermal chamber to manipulate temperature and see how it performs. First test, we have the two White Rabbit devices, the optical fiber, everything within the thermal chamber, and we start playing with the temperature. So first test, we have the temperature set at 5 Celsius degrees, and we see the histogram of the offset that we obtain with White Rabbit. What we will expect, this is around plus minus 100 picoseconds, so pretty good result. We are achieving the sub-nanosecond, which is the goal, and the excursion that we have, the stability is quite good. Then we decide, OK, let's play with temperature. And we do a transition from 5 degrees to 40 degrees, so a 35 degrees Celsius transition. And what we see is that when the temperature chamber heats, we start getting a second loaf in the histogram. So we see how the change on temperature actually had an impact on the offset that we were able to achieve. In this case, I mean, it's not probably very critical for most applications because we are shifting from a mean value around 350 picoseconds to a mean value around 225 picoseconds. So probably not a big deal for many of you. It's a big deal for me, OK? I care about that. So then it's like, OK, we see that if we have the white rabbit devices and the fiber in the chamber, we have this effect. Let's get the endpoints, the white rabbit devices, out of the chamber, and let's get the optical fiber only in that chamber and see how it affects. And here, which is the cool thing about this technology, we saw that we didn't see this transition between one loaf and the other. So we were able to change the temperature, still maintain the same accuracy in both scenarios. So that indicates that the problem is not with the fiber itself. We can hit that. It's probably on the endpoints or the transceivers that we are using. So we decided testing the transceivers, different temperatures, and check the actual wavelength that they were transmitting. And we saw an evolution with different temperatures. If we relate that evolution of the wavelength at different temperatures against the offset that we were calculating, that we were measuring, we see a linear relationship between the two of them. So that indicates that maybe we can do some things at the software level to compensate for temperature transitions on the SFPs, which seems to be the most important thing. And we are able to remove the influence because of the optical fiber. So there's a lot more to test. If you want to work with high accuracy, explore a little bit about White Rabbit, I'm happy to have conversations on that topic. And of course, please engage with the OCP Time Appliance project. We are collaborators. It's a very nice community. So more than happy to have you on board. Okay, thank you.
Thank you, Paco.